Okay, so I'm going to start relations. Yeah, certain parts of relations. So, first of all, before we start looking at this question, we're going to have to say what is a relation? A relation is just a mapping, in short, a mapping between two values. So, like in this question, we've been told that we have x, r, or y. X, r mean well, a relation between x and y, right? If x is a factor of y, right? So, in fact, let me just read the full question. So we have our a here, right? Which we have a, which is this one, and r being the relation on a, right? Then if x and y are in r, are in a, right? So if x and y are members of a, then this is a relation that defines them. To say, okay, x relates to y if x is a factor of y. Then we've been taught to map this to list this relation, right? So I'm going to start off with just a, right? Going to view this relation. This relation now. So it's a set first of all of two pairwise of pairwise things. So over here we're going to have our first one. So we're going to start off with one. One is a factor of one itself, of course, right? Followed by one being a factor of two, and basically one is a factor of everything here. One is a factor of 6. One is a factor of 12, 16, and then we have 24 there, right? We have that there. Then now we're going to say, okay, we go to 2. 2 being a factor of itself, right? Then 2 comma 6, 2 comma 12, 2 comma 16, 2 comma 24. We have that there. Then we're going to have 6 comma 6. Then we're going to have 6 comma 12, and then we're going to have 6 comma 24. Then we have 12 comma 12, then 12 comma 24, then we're going to have 16 comma 16, and finally we're going to have 24 comma 24. Right, we have that there as our relation. Right, this is our relation. So x being a factor of 1, we know this here is our x, this is our y, and if you look at all these, the x is a factor of y. So we have that there. Now we're going to show that the relationship is a partial order. Now what does that mean, right? If a relationship is a partial order, so a partial order or a poset, right? A partial order, basically what this means is that it means a couple of things. First of all, it means that this is reflexive. And what reflexivity is, right? What reflexivity basically is that for each and every x, right? For each and every x that's a member of a, x comma x should be a member of r, right? This is what we mean when we say reflexivity, right? If we have this being reflexive, right? So all these elements, they should map to themselves. In short, we should have 1 comma 1, a 2 comma 2, a 6 comma 6, a 12 comma 12, a 16 comma 16, a 24 comma 24, right? Then we have symmetric, right? Oh, it should be anti-symmetric, sorry. What being anti-symmetric means is for each and every, right? For each and every x comma y that's a member of a, right? If x is not equal to y, then x comma y should be a member of r. So if x is not equal to y, and if x is not equal to y and x comma y is a member of r, then y comma x should not be a member of r. Where this antisymmetric comes from, it comes from the definition of symmetric, which is basically if you have x comma y being in a, right, then x comma y should be a member of a relation, same as y comma x. Y comma x should also be a member of that relation, as long as x comma y are members of a. Right? If you have x and y being members of a, then if the relation is symmetric, x comma y should be there and y comma x should be there. But for antisymmetric, we say this guy should not be a member. Basically what we mean by antisymmetric, as long as those two are not equal to each other. So for antisymmetric, we allow elements that are equal to each other to exist, right? 1 comma 1, etc, etc, right? Then transitivity. What transitivity means that if you have x comma y comma z being members of a, right, x comma y, and let's say if x comma y is a member of r and y comma z is also a member of r, then what we should then have there is x comma z being a member of being a member should be a member of R. So if you have this and that being members, then this here mapping there should be a member. So now how do we go about to prove this one, right? So let me just bring up that question again on the next page, right? So how do we go about proving that, okay, our friend there let me do this, have that there, then I'm going to just copy this entire thing because I'm going to need it anyway. Yeah, just going to have that there, so I'm going to make reference to this. Okay, so first of all, want to show that it is reflexive, right? So for B, so case number 1, reflexive. Does this work? So for all the elements, we remember in our thing we have 1, 2, 6, 12, 16, whatever. Reflexive, does each of the elements in our set map to itself? 1 maps to 1, right? 2 maps to 2, right? 6 maps to 6, 12 maps to 12, 16 maps to 16, 24 maps to 24. This is true, it is reflexive, because for each and every x that's a member of A, x comma x is a member of R. We have that there. What's the next thing? The next thing is antisymmetric. Antisymmetric, right? Is this antisymmetric? First of all, remember antisymmetric, the definition. So we look for elements that are not the same. So if we have so for antisymmetric, we allow elements that are the same to map together. So the 1, 1, 2, 2, of course it's reflective, so those are there. But then if we start looking at elements like 1 to 2, do we have 2 to 1 there? No. 1 to 6, do we have 6 to 1 there? No. If we have 1 to 12, do we have 12 to 1 there? No. 1 to 16, it's not there. That's not there. We don't have the opposite of we don't have 2 to 6, we don't have 6 to 2, we don't have 12 to 2, we don't have 16 to 2, and so on and so forth. So basically we don't have these the values here mapping back to this, right? We don't have that in our we don't have this in our relation, right? So we only have x to y, but we don't have y to x, unless of course those are the same. So this is antisymmetric. Is this transitive? This is transitive, right? So for transitivity, so we have 1 to 1, but do we have we have 1 to 1 and then we have 1 to 2. Of course we're going to have 1 to 2 there. So all these are start off with a 1. First of all, they are transitive. Which one am I going to take an example of here? Okay, so we start off by, okay, so I'm going to show you how you list these things if they are transitive, and then you can complete the table. Because yeah, it's going to take time, because this is a very big thing. Yeah, so for the most part we're going to have x comma y, and then we'll have y comma z, right? So then we're going to look at this, right? Please, there's no need for me to even come and prove them, because basically as long as it's there. Okay, this one. Okay, we're going to look at 1 to 2, right? So we have 1 to 2, and then we have 2 to 2. So 2 to 2 is already there, right? So this is x to z, right? So then I'm going to have, okay, I have 1 to 2 and then 2 to 6, 1 to 2, and then I have 2 to 6. We have a 1 to 6 there, right? We have a 1 to 6. I have 1 to 2 and then 2 to 12. A 1 to 12 is already in our set, right? Okay, it's just 1 to 2 here. We have a 1 to 2 and 2 to 16. We already have a 1 to 16. So a 1 to 16, a mapping between that and that is already present in our thing. I have a 1 to 2 and then a 2 to 24. I have a 1 to 24 in my set there, right? And then you continue this for all of them. So let's say for instance we have a 2 to 2 and then a 2 to 6. The 2 to 6 is already there. In fact, for these that are the same, we can even just avoid them for now. I have a 2 to 6, right? I have a 2 to 6, and then now I have a 6 to 6. Of course, I have a 2 to 6. I have a 6 to 12. Of course, I have a 2 to 12. Is that 2 to 12 there? If I check, yes, I have 2 to 12. I have 2 to 12, and then I have, let's say, 12 to 24, right? Is this guy present? Yes, we have a 2 to 24 in our thing. If I have a 2 to 16 and then a 16 to 16, that is a 2 to 16 is already there. What can I get here? 2 to 24, 24 to 24, that's already there, it's fine. But yeah, you just have to keep going. So let's say if I have a 6 to 12 and then I have a 12 to 24, do I have a 6 to 24? 6 to 24 is right here, right? So this is transitive, so you can keep on filling in that table by just listing the x to y and then your y to x, and then trying to show whether you have your x to z there. As long as you can show that, then you can show that okay, that thing is transitive, right? That's the basic definition of transitivity. But we're going to then do something now. We're going to draw a Hess diagram. So that's why I'm going to show you how to draw a bar graph, which isn't what we've been asked to draw in this question. But then I'm going to show you how to move from that bar graph to a Hess diagram, right? So now, this Hess diagram, again, how you draw these graphs, it's mostly up to you, I can say. But again, I'm pretty sure there are rules that you can follow for these things. But basically, we have how many numbers do we have in this thing? We have 1, 2, 3, 4, 5, 6. So each of these numbers is going to represent a point, right? So I'm going to draw them like this: 1, 2, 3, 4, 5, 6. And this is just how I've decided to draw it, and you'll see why. So let's say this is our 1. This is my. I'm going to use different pen. So this is going to be 1. This is going to be 2. This is going to be 6. This will be 12. This will be 16. This will be 24. Right? We're going to have it like that. I hope this is clear. Then I'm going to start drawing my arrows. Right? So first of all, we start off with drawing them as they are. So 1 to 1. Basically, this is an E. We're basically saying 1 maps to itself like that. Right? What's 1 to 2? 1 to 2, we're basically saying it maps like that. 1 to 6, we're basically saying that. Right? Then now we're going to say, okay, 1 to 12, this is what we're saying. 1 to 16, we're basically saying that, we're basically saying that. And then 1 to 24, we're basically saying there is an arrow that goes there. Right? So that's 1. Then we're going to have 2 to 2. We're saying that 2 maps to itself. And remember, this isn't a Hess diagram. This is a bar graph. Yeah, I'm going to show you how to move from this to a proper Hess diagram. Then we're going to have, okay, 2 maps to itself, then 2 maps to 6, like that there, right? Then 2 also maps to 12, right? Okay, we have that there. And of course, from these graphs, you can even see transitivity. So I have 1 to 2, and then I have 2 to 6. Of course, then I'm going to have 1 to 6 as my transitivity there. So you can just tell from these things. I have 1 to 2, and then I have 2 to 12. Of course, I'm going to have 1 to 12 there, and yeah, so on and so forth. In fact, also we're also going to need a 2 to 16 there. Again, transitivity. You can basically tell transitivity from these things. So that's transitivity there. Okay. Then now, so we've mapped up to this point. Then we're going to have the 6 to 6. Then 6 to 12 is there, and then 6 to 24. Right? Then we're going to have our 12 to 12, which is that E there, right? Then we're going to have our 12 to 24, right? 12 to 24. Then we're going to have our 16 to 16 there, which just maps onto itself. And then we're going to have our 24 to 24. This is a bar graph. Quite messy, but yeah. So now the purpose of a Hess diagram is just basically saying we're going to get rid of most of the stuff that we don't need to show. Because for instance, we know that Hess diagrams are used to represent posets. Yeah, if I remember correctly, Hess diagrams use them to represent posets, and we already know the properties of a poset. It will be reflexive, it will be antisymmetric, and it will be transitive. So I mean, there's certain things we don't even need to show. We just need to show that this maps to this maps to this maps to this. That's all, right? There's certain things that we don't even need to show when it comes to mapping these guys, right? So we're going to come and remap this guy, right? I'm going to redo that. So I'm going to redraw it again. In fact, to redraw it, I'm going to move the 2 here and the 6 here. I'll show you why. Yeah, so I'm just going to move things around. I'm going to leave this as 6, this as a 2, this as a 12. Again, there are multiple ways you can do this. In fact, yeah, there are multiple ways we can do this. We can almost draw it like a straight line. Even we can say we can put our 24 here, then I can put my 12 here, I can put my 6 2 1. So 24 12 6 2. Then I'm going to put my 16 here. I'm going to show you why I did this in a moment. So this was a bar graph. Then 1 2 6 12 24, and then this over here is what's this? This is my let me put it here. Let me move it here. Let me move it here. There are certain rules that I'm forgetting, but yeah. So now we're going to then just draw this diagram, right? To draw this, we know that, okay, we're going to, first of all, it won't include any of these ears, right? Also, it won't include any of the transitivities. So things that will cancel out. First of all, we have 1 to 2, and then we have 2 to 6, right? That. So we don't need this transitivity for that, right? We have 1 to 2, right? We have 1 to 2, and then we have 2 to 12. So we don't need this transitivity here of 1 to that. Most of the lines that are connecting outside of 1, we won't need them because most of these are just transitivities anyway. So none of these lines will be needed. Well, that there and that there. This one again, we have 2 to 6 and then 6 to 12. 6 to 12. We don't need this line. We have 2 to 6 and then 6 to 24. We don't need this transitivity here, right? So for the most part, majority of our transitivities, we won't be needing them. We have 6 to 12 and then 12 to 24. We don't need 6 to 24. Also don't need this line. So basically, if you remove all those lines, basically you're just going to have, we're going to end up with, let me even use a straight line to there. We're going to end up with a 1 to 2, right? From that 1 to 2, we're then going to have a 2 to 6. And we're going to have a 6 to 12, and then we'll have that there. Then we're going to have a 2 to 16 there. This is our Hasse diagram. From this, again, if I was to tell you to say, okay, this lists factors, right? 1 is a factor of another. We know 1 is a factor of 2, 6, that and that. We know 2 is the only factor, 2 and 1 are the only factors of this. 2 is a factor of this, this and this. 6 is a factor of this and that. 12 is a factor of that. So basically we have that. So we can avoid all the transitivities by saying, okay, no, I have to put a transitivity here, I have to put a transitivity there. Because if we were to try and reintroduce those transitivities again, because we even remove the arrows, because if we were to try and reintroduce the transitivity, we'd have, okay, that goes there, right? That goes there. It also goes here, and it also goes there, like that. Then this goes here, this goes there, this goes all the way there, this here, this there, stuff like that. So basically, this is why we draw the Hasse diagrams. This is why they exist, to basically remove all that, because we already know the rules, right? We already know the rules of this kind of, we already know the rules of a poset and a Hasse diagram. So no need for us to introduce, for us to draw any of that stuff. We can just say, we already know it's there, right? We already know it's like this. As long as you know the definitions, you can always move from this to something like this. It's fine, right? But we just don't put them there, and this is more readable. So this is our first question in relations. I'm going to do another one, and then we can go on to functions and Boolean algebra.